Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. Now, this paper which I am dealing with is physics of materials, and I am doing the section on bondings in solids. The contents of today's lecture, that is lecture 11, will be as follows: comparison between different bonds, origin of X-rays, targets used for producing X-rays, and X-ray diffraction studies. And the title of the talk will be comparison between different bondings and partly X-ray diffraction. Now, we will move on to the comparison of different bondings. This especially I am doing because I have been telling you in the last lectures about mixed bonding. You may be surprised to know that in some solids all the 4 bondings, the 3 primary bondings, ionic, covalent, metallic, and the van der Waals bonding, secondary bonding, all the 4 bondings being present in some solids. It is one of the things which of course, as students of electronics or students of material science should be knowing, that the mixed bonding has come to stay. It is a very important aspect. So, let us now talk of mixed bonding. Some solids which combine different types of bonding are tabulated below, and you have the intermediate ionic covalent bonding. As I told you in the previous lecture, let us take gallium arsenide. It is a mixed bonding. It is gallium arsenide, just because it is a semiconductor, you should not be tempted to tell that the bonding is covalent, right. In pure silicon and germanium, the bonding is fully covalent, but in solids like gallium arsenide, cadmium sulfide or indium telluride, the bonding is covalent cum ionic. I told you in the last lecture how the fraction ionic character can be calculated. Therefore, cadmium sulfide TiO2, again gallium arsenide, as I told you, cesium oride. Now, can you tell about cesium oride? Now, cesium oride is one of them very important material, in the sense that you may be perplexed to know that you are combining what cesium. Cesium is a metal, right, the periodic table. Where do you find cesium? Cesium is the first group, right. You have got lithium, sodium, potassium, rubidium, cesium, the first group element. It is a metal. You know that all of you know that gold is a metal. A metal and another metal, when they are combined, what will you get? This is called cesium oride. The name cesium oride, you should be able to, from the name you should infer it is something like sodium chloride or cesium chloride. See, even though it is a combination of two metals, you may be surprised to know that it is a insulator. A very rare example, a combination of two metals giving rise to a wide gap insulator. So, it is reason, that is the reason why it is called cesium oride, right, like cesium chloride. So, a combination of two metals need not be metallic, right. It is a very unusual case. Cesium combined with gold gives rise to cesium oride. It is a wide gap insulator. It is a very interesting example. Then intermediate ionic, covalent and van der Waals. The three bondings are present in CdI2 cadmium iodide. Then ionic and metallic are present in niobium oxide and titanium oxide. Then ionic, metallic and van der Waals, all the three bondings are present in zirconium chloride. Then ionic, covalent, metallic are present in some of the systems like this, which are coming under oxidized platinum chain compound. Then you know graphite has the three bondings, covalent, metallic and van der Waals. You know graphite is flaky in nature, because graphite is a simple hexagonal structure, and it will be used as a lubricant, because you got van der Waals bonding between the top plane and the bottom plane in the hexagonal structure. Between the top and bottom, the bonding is van der Waals, weak van der Waals bonding, that leads to the sliding of the layers one over the other. Graphite is, that is the reason why graphite is used as a lubricant. So, the van der Waals bonding is present in the plane. You have got covalent come metallic. So, graphite is an example where the three bondings are present. Now, the more importantly, as I told you earlier, all the four bondings are present in some systems like TTF, TC and Q, the details of which can be seen elsewhere. There are some other systems like TTF, TC and Q, which have all four bonding mechanisms being present, right. Now, therefore, the conclusion is, now you know as on date in very many systems, right, very many solids, the high temperature superconductors, or you have nickel aluminides, which are used for aircraft turbine blades, engine blades, right. Now, in all these systems the bondings are or gallium arsenide, it is a semiconducting system, but even though it is a semiconductor, the bonding is not fully covalent. Now, therefore, we are in a era of mixed bonding, right. Very many systems have mixed bonding. Now, let us go to the bond strength. Now, because we are almost come to the summary part, end of the different bondings, we have to compare the primary bonding and the secondary bonding, the bond strengths. The bond strength in the case of primary bonds, it varies from 0.1 to 10 electron volt per bond. Per bond means to break the bond, you have got an atom here, the bonding is there. You have got a, say, take the case of hydrogen atom, you have got a proton and electron. The electron is bound to the proton by what energy? 13.6 electron volt, that is the bonding, that is the binding energy, right. Similarly, the bond strength or the bond energy that exists between, in the case of primary bonds, it varies from 0.1 to 10 electron volt per bond. On the other hand, in the case of secondary bonds like van der Waals bond or hydrogen bond, the bonding strength ranges from 0.01 to only 0.5 electron volt. Instead of 10 electron volt, the maximum value ends with a value like 0.5 electron volt per bond. They are the secondary bonds. Now, secondary bonds are also of great importance, especially when we are talking about nanoparticles, nanomaterials or nanostructure systems. The van der Waals bond plays an important role, and in biological systems like DNA and so on, again the secondary bond, hydrogen bond is important, right. Hydrogen bond is important, and similarly van der Waals bond, the secondary bonds also, they are very important in certain systems, as I mentioned just now. Now, let us go through the properties of ionic solids in a greater detail. Once again, ionic solids are made up of metallic and non-metallic elements. Can you tell me the example? The simplest example, all of you know, you have studied even in high school, that NaCl is the simplest example for a ionic solid. NaCl, what do you know about Na? Na is metallic, chlorine is non-metallic. You look at a periodic table, Na is the first group, sodium is a metal, cesium is metal. So, cesium chloride or sodium chloride, a metal atom combined with a non-metal atom gives rise to an ionic solid, right. The details of which we have seen already, and so the thing is ionic compound is made up of a combination of metal and non-metal, right. Then ionic solids are hard but brittle, right. They have high melting points. They are soluble in polar solvents like water and ammonia. These solids are insoluble in non-polar solvents. Ionic solids, will it conduct electricity? You know, in an ionic solid, what do you have? You got a positive ion, negative ion, positive ion, negative ion. You do not have free electrons, right. So, only if free electrons are present, there will be electrical conduction. So, ionic materials do not conduct electricity, but upon heating, even the ions themselves will start moving. Instead of electronic conductivity, you will be having what is called ionic conductivity. That will take place only at high temperatures. At normal temperature, ionic solids are insulators. They are called ionic insulators. Ionic solids are generally insulators. They do not conduct electricity because you do not have free electrons, right. Therefore, as I told you, however, ionic solids dissolve in water and the solution conducts electricity. You know, the solid state ionics, or you can have in the ionic solids heated to melt high temperature. In the molten state, the ions themselves will start moving, giving rise to what is called ionic conductivity, but electronic conductivity cannot be expected in ionic solids. Ionic solids are transparent in visible radiation. It exhibits characteristic absorption peaks in IR regions, infrared regions, right. In ionic crystal, an anion is surrounded by as many cations. You have got a anion, then the cations will be present here, and each cation will be surrounded by anions. Okay. Now, the bonding is non-directional bonding, right. The bonding is not, because you have got ion here, ion here, ion here, and so the negative ion, positive ions surrounded by negative ions, negative ions will be surrounded by positive ions. So, it is a non-directional bonding. Okay. Then let us pass on to the covalently bonded solids, right, some of the properties, right. Now, when you go to covalently bonded solids, as we have seen repeatedly, the simplest is the hydrogen molecule, right. When you combine two hydrogen atoms, you get the hydrogen molecule. What do you find, or how does you explain the stability of hydrogen molecule? It is because of covalent bonding. So, the sharing of the electrons. So, what is hydrogen? In the gaseous state. So, H2, O2, they are gases. So, the covalent bonding is present in gaseous materials. In a liquid like CCl4, you have got covalent bonding. In solid materials like silicon, germanium and tin, and you know, especially silicon, germanium, you have got covalent bond. Tin is a metal, right. In solids, they exist in crystalline state, because you know silicon, germanium, they are crystalline materials. And again, I will come back to a comparison between silicon and germanium. All the electronic students will have studied in detail the solids like silicon and germanium. They are fully covalently bonded solids having diamond structure, and a comparison will be made to understand as to why some of the several devices which are being used today are silicon based and not germanium based. And so, I will come back to the case of silicon winning over germanium, right. I will come. Let me now pass on to some of the other properties of covalently bonded solids. Covalent crystals are usually hard and brittle materials with high binding energies. Diamond is an example of having high binding energy. You got a energy gap is 7.4 eV, right. The melting point, boiling points of covalent solids are usually low as compared to those of ionic solids. The exception being diamond is having a high melting point. Covalent bond is a directional bond or two silicon atoms, right. The bonding is directional, highly directional. They generally dissolve in non-polar solids such as benzene, toluene, etc. However, some covalent bonds, compounds like HCl, NH4 are soluble in water. Basically, all covalent crystals are insulators because of the non availability of free electrons. You know very well that to induce current in a semiconducting system or a semiconducting diode, or you have a p-n junction and p-n-p junctions and so on. So, why do you make a p type or n type material? To induce current, to introduce more electrons or more holes, right. That is the reason why you make dopants and so on, right. Use the dopants, introduce dopants in the material. Now, therefore, left to themselves, silicon or germanium, they are semiconductors or insulators, right. What is the difference between a semiconductor and insulator? Nothing. The only thing is insulator, the band gap is large. Diamond has got a 7.4 eV, the gap is large. Semiconductor, the energy gap will be lesser, right. But otherwise both are same, right. I mean qualitatively they are same, but quantitatively the energy gap will be smaller. They are semiconductors, and of course, these crystals are transparent to long wavelength radiation and opaque to shorter wavelength. Covalent bonds may be polar or non-polar in nature, depending upon the fact that whether the electron pair is unequally shared or equally shared. In HCl, it is unequally shared, or H2, as I told you, the sharing of the two electrons only equally shared, right. So, these are some of the properties of covalently bonded solids. Now, we come to a very important question, namely, of the two parent crystals, basic semiconductors like silicon and germanium, an electronics student may ask, why should you prefer silicon, or why can't you prefer germanium, or the other way around, why can't you have why can't you prefer germanium, or why can't you prefer silicon, and so on, right. Now, prior to 1960 or up to 1960, germanium ruled. Many semiconducting systems were made up of germanium, but in 1960 onwards, by the end of 1960, practically all computer logic designers, they switched over from germanium diodes to silicon transistors and diodes, right. A very important thing. Now, what makes them to go from germanium to silicon? That is a nice article written by Schneider. Silicon devices became important compared to that of germanium because of the following factors: high switching speeds or superior switching speeds, then rectification efficiencies, high breakdown voltages, and power dissipation ratings. Depending upon the four factors, the switching speeds, rectification efficiencies, silicon rectifier, right, and breakdown voltages and power dissipation ratings. Now, these things make silicon to be more superior compared to germanium. So, as on date, in most of them integrated circuits, most of the computers and very many other silicon rectifiers, MOSFET and so on, very many devices which are being used are made up of silicon rather than germanium. But one should know it is generally difficult to prepare germanium, because silicon wets and reacts almost with all the containers. So, one makes use of what is called a floating zone method to prepare silicon. So, preparation of silicon is somewhat difficult. In spite of it, mass production of silicon based systems devices have come into the market, which are found to be cheaper. And again, where from you get silicon? It is silica. Our mother earth contains sand, sand is SiO2, silica. So, the abundance. So, the abundance of silica makes it another important factor. It is cheaper, right? It is cheaper. That is the reason why you go to silicon rather than to germanium. So, prior to 1960, germanium ruled, and very many scientists who have been associated with semiconductors like Bardeen, Shockley, Brattain, they shared the Nobel Prize for the invention of transistor. They had they did immense work and showed that a passive layer of silicon or a thermally grown oxide layer can be formed on silicon SiO2, silicon dioxide. Silicon, you can have over silicon, a oxygen layer will be formed obviously, right. Copper exposed to air will, what will you get? Copper exposed, any metal exposed to air will be, you will be having oxide layer automatically formed, right, because of atmospheric air, oxygen will be sitting, and so copper, you will have copper oxide, cupric oxide or cuprous oxide and so on. So, oxide layer will be formed on the material. Similarly, you got silicon dioxide will be formed on silicon. Now, that thickness is not sufficient for certain reasons for device applications. Now, therefore, you prepare what you call thermally grown oxide layer is formed, a thick layer is formed for certain applications. Therefore, because of these factors, silicon is preferred over germanium. Now, this is a very important thing, a basic electronics student should be knowing why silicon is preferred over germanium, right, that is important, right. Then properties of metallically bonded crystals. The metallic bond is a weaker bond compared to ionic and covalent bonds. Metallic crystals have crystalline structure, all the metals have got the atoms are properly arranged. They have high thermal and electrical conductivities. All of you know the Weidmann-Franz law, which is the best conductor in the whole of the periodic table, which is the best electrical conductor. The best electrical conductor is, is it copper? The best electrical conductor is silver, but unfortunately, you cannot have silver wire for for transferring current from a particular thermal station to some other place, to your native place. You cannot have a silver wire because silver is very costly. Okay. Therefore, you make use of copper wire, right. So, the noble metals are good conductors, but the best conductor of electricity is silver and not copper. Okay. But next is copper comes later, but the point is mostly the noble metals are very good conductors of electricity. Not only they are good conductors of electricity, the Weidmann-Franz law. Now, therefore, very good electrical conductors should also be very good thermal conductors. So, the thermal conductivity of silver should be very high if you believe in Weidmann-Franz law, because electrical conductivity is high, thermal conductivity also should be high. Okay. They have high electrical and thermal conductivities. How do you explain the electrical conductivity? What is meant by current? Current is nothing but the flow of electrons. So, in metals and alloys, you have got free electrons, right, because from every atom you have got core electrons. Now, the valence electrons become free and they take part in the conduction, the electric and thermal conduction, and so the current transport in metals and alloys are due to these free electrons. The other properties are the melting and boiling points of metallic solids are lower than ionic covalent solids. Metallic bond is again, is it directional or non-directional, because the electrons can flow in all directions, right. Okay. Therefore, generally, so the metallic bond, if you do not apply any electric field, electrons will be going here and there, right, random movement of the electrons. The bonding should naturally be non-directional, right, the non-directional bond. The metallic crystals are opaque to light. You take a solid copper, right. You pass light, it is opaque, right, it is not transparent. Metallic solids are not soluble in polar and non-polar solvents. Metallic solids are soft and malleable and ductile, right. Ductility is again a very important property. They are ductile compared to your silicon, germanium, they are brittle, right. So, the metallic materials, alloys are ductile. Ductility is very important, right. You have heard of ductile brittle transition and things like that, and the the failure of Titanic ship and so on. Now, therefore, the material should be ductile, at low temperature, high temperature and so on. So, then we pass on to the properties of dipole bonds. Dipole bonds are much weaker than primary bonds, but are stronger than the van der Waals or dispersion bonds. Thus, these are weakly bonded solids. These bonds have directional properties. Solids with dipole bonds are good insulators, since there are no valence electrons. You look at HCl, you do not have any valence electron, right. SO2, they are the gaseous state. Water is again a secondary bond, like a hydrogen bond. Then you go to the properties of hydrogen bonded solids. What do you mean by hydrogen bonded solids? One of the atoms which is participating in hydrogen bonded solid should be hydrogen, right. Hydrogen should be there, and hydrogen bonded solids have low melting points. As I told you, DNA is a good example, right, wherein you come across the hydrogen bonding. Hydrogen bonded solids are very good insulators, since no valence electrons are present. The hydrogen bonds are directional, and some of the other properties are they are soluble in both polar and non-polar solvents. They are transparent to visible light. Since elements of low atomic numbers for such solids, they have low densities, right. And you come to lastly the van der Waals bond. The van der Waals bond, as I told you, is purely of quantum mechanical origin. The van der Waals bonds are again non-directional. Solids with van der Waals bonds are insulators, since no valence electrons are available. Solids are soluble in polar and non-polar solvent. They are transparent to light. Van der Waals bonded solids have again low melting points. You have the examples of van der Waals bonding, like solid argon, solid neon, xenon, all the inert gases, they crystallize because of the van der Waals bonding. We have to move on to the X-ray crystallography. What do you do using X-ray crystallography? We will study the positions of the atoms and the bondings in these solids which I have been talking about using X-rays. So, there comes the X-ray crystallography. Let me now summarize what we have learned so far from today's talk. The primary bonds have bond energies varying from 0.1 to 10 electron volt per bond, whereas the secondary bondings have the bonding energy varying from 0.01 to 0.5 electron volt per bond. There are many systems which I have shown, they have mixed bonding, right. Thank you.